did postdoc in several institutions in USA, and he had collaboration in International Center of Theoretical Physics for a long time, and he visited University of São Paulo a couple of times and had several collaborations with Professor Silvio Canuto and Arnaldo Gamal. And now she is currently working in the group of Professor Barnali Chakrabarti and University of São Paulo, São Carlos. And she will be presenting the colloquium today. We'll be talking about quantum simulation with ultracold boson impact of long-range interaction. Okay, I invite Professor Barnali.
Well, good afternoon, everybody. Thanks for the introduction, and it's a great pleasure for me to be here with you. Well, the topic I am going to talk about today is the quantum simulations with ultracold bosons. And I also discuss the impact of long-range interaction because this is the main research project I am working right now. This is a brief outline. I will talk about preliminary overview about the quantum simulation, only the analog simulations. Then I will present some perspective of ultracold atoms related with the low temperature physics. Just to emphasize that how the platforms of ultracold atoms has been gradually became the most versatile platforms of quantum simulations. I will discuss two specific cases like simulations with Bose-Hubbard model and the Fermi-Hubbard models. Then I will switch over to the present situations of the different many-body approaches, but I will discuss in little bit details about the multi-configurational time-dependent Hartree for bosons or fermions. That is the methodology which I utilize for my ongoing research. I will present some of my recent results with long-range interactions. Then I will conclude the summary. Okay. Let's start with the vision of Feynman. What we actually mean by quantum simulator. Quantum simulator is a control systems which you can use to simulate other quantum systems which is otherwise difficult to probe, or in some cases it is impossible to probe. Well, with these schematic representations, you can get some idea about quantum simulations. On the top, I have the quantum systems, which is difficult to probe. Phi, it is the quantum states of this quantum system, which is being evolved with time under this unitary transformations U. I cannot probe these quantum systems for many reasons. But the idea of quantum simulator is like this, that I can probe this system now in this synthetic platform, which I call it as the quantum simulator. And the quantum states of this quantum simulator is psi, which is also being evolved with the time t under a new unitary transformations U primed. So the idea is, in this quantum simulator, some way I will have much more flexibility such that I can tune the experimental parameters, or many other tuning is possible, manipulations in the states is possible. So I can do the measurements in these states and then go back to study what is going on inside this actual quantum system. But the whole logic is applicable only when these kinds of the mapping exists between the quantum systems and its simulator. So this is the basic idea of the analog simulator. That means where you basically implement a Hamiltonian in your physical system and just look for its ground state or the dynamical evolution. Of course, when we talk about quantum simulations, also there is a digital simulations where we talk about the gate-based approach, but I am not the right person to talk about digital simulations, which is mainly related with the quantum computations. But the idea of Feynman can be visualized in some other ways. He said that you can implement a synthetic system in your laboratory. This synthetic system can implement any Hamiltonian, and these Hamiltonians can be related with some approximate real material, or it may be something abstract quantity. But these synthetic abstract system must have enough flexibility such that you can tune your parameters. Let's give an example. Suppose I like to see what will be the effect of interactions in the phase diagram. In the real material, I don't have much flexibility. I cannot change the interaction state at my will, but I can do in the quantum simulator. But when I am talking about some synthetic systems in my setup, this synthetic system is also an independent system. It has its own properties, so it may be also challenging in some other ways. So the other way Feynman tried to give the message that these kinds of the simulation gives you some idea about quantum many-body physics. But the idea of Feynman was limited in the theoretical point for a long time, because until the laser cooling and the Doppler cooling has been developed completely around 1980s, there was no possibility of how to do the manipulations in the quantum states. Finally, we must say that the simulations is related with the low temperature physics. And this is a brief history. I just point out few milestones from them. You know that the temperature range of the Kelvin, it led to the realizations of the superconductivity in 1911, superfluidity in 4 helium in 1938, and then much lower temperatures order of the millikelvin basically led to the realizations of superfluidity in 3 helium in 1972. And then finally, we have the ultra-cold temperatures after achieving the Doppler cooling and the laser cooling technique in 1980s and above that. And these cooling mechanisms basically lead the realizations of Bose-Einstein condensations. This ultra-cold temperature means it's order of the microkelvin and nanokelvin. And with this Doppler cooling technique, it was associated with the evaporative cooling and magneto-optical trap. And finally, the Bose-Einstein condensations was realized in the ultra-cold quantum degenerate Bose gas by the 3 research groups in Gila, MIT, and Rice in the year of 1995. The idea of Bose-Einstein condensations was like this. It was put forward in 1924 and 25. That you have if you have a collections of the bosons, and if you go on decreasing the temperature gradually, at some low critical temperature, we do not know what is the actual value of the temperature, but at some critical temperature, the bosons will settle in the ground state. Then it took almost 70 years to achieve experimentally in the year of 1995. We know the reasons. The reasons was how to avoid the conventional condensation process. It was the major challenge to achieve BEC in the real experimental platform. Because when you try to cool down your systems, the atoms, they undergo 3-body process and they form the molecules. Once they form the molecules, they are immediately lost. Because Bose-Einstein condensations means you are basically allowing the bosons to settle in the ground state, but don't allow to form the molecules. The atoms, they will carry their own quantum identity. So the immediate solutions for the physicists was, okay, make it dilute. How much dilute? It should be maybe 100,000 times smaller than the density of the air. But at the same time, it caused ultra dilute, ultra low temperatures, which was order of the nanokelvin. And finally, it took such a long time to achieve it experimentally. The ultra-cold quantum gas became the first platform to achieve the Bose-Einstein condensations. You can see all these are the alkali atoms. Well, after the realizations of the Bose-Einstein condensations, theoretically, especially the mean field and the other parallel experiments were mainly confined in the coherent matter waves, weakly interacting Bose-Einstein condensations, or molecular BEC. But in 1990, there is another milestone, that is the achievements of tunable interactions by introducing the phase-back resonance. The term phase-back resonance, it's a common word in nuclear physics. And this idea was put forward in the platforms of ultra-cold trap atoms, that here you have the magnetic field. Just simply tuning the external magnetic field, one can able to tune the scattering length very high. What does it mean? It means that very easily we can make the scattering length much, much larger than the interatomic spacings. That means when the scattering length is very high, that means now we can talk about the strongly correlated phases. This is very interesting physics, because generally strongly correlated phase, this term is applicable for dense systems like nuclear physics, like condensed matter. But our platforms is the ultra-cold and ultra-dilute regime. So the phase-back resonance basically makes a lot to determine the futures of these ultra-cold atoms, because now we can talk about the strongly correlated phases even in this ultra-dilute regime where I have the quantum degenerate gas. The next milestones in the achievements of the optical lattice. When we talk about the real solid, real material, we say that, well, the electrons, they are moving in the periodic lattice. And this periodic lattice, it is created by this periodic array of arrangements of the atom cores. We cannot probe everything, how the electrons are dancing in the material. We do not know, because we cannot probe these systems in our setup. But optical lattice is the alternative platform, where just simply superimposing the laser beam externally, we can mimic, we can emulate the actual lattice structures in these optical platforms. We call it optical lattice because the superimposition is for the laser beams. And when these atoms, they're being trapped here, they are trapped due to the optical, just the dipolar forces. So this optical lattice is basically emulating the actual crystal lattice in our ultra-cold setup. However, this optical lattice has much more flexibility. You can change the dimensionality of the systems. By superimposing the laser beams in different directions, you can produce the different lattice of different geometries, hexagonal lattice, super lattice, even the spin-dependent lattice. At the same time, if you change the angle of this superimposing laser beam, you can basically introduce topology, you can tune the band structures. So it's a lot of flexibility, and due to this, we conclude that the atom in the optical lattice is the most versatile platforms in the condensed matter systems. However, I think that the idea of quantum simulations with the strongly correlated states of matter goes back to 1998. That was the pioneering work of Jaxos, Chirac, and Zoller. In 1998, the basic idea was like this, that if we can load these optical lattice with the ultra-cool atoms, that may be another platform to realize the quantum phase transitions. What is quantum phase transitions? When you have ultra-low temperature close to 0, there is no thermal fluctuations, but there is quantum fluctuations due to uncertainty principles. And these quantum fluctuations basically leads to the quantum phase transitions. And the idea of Jaxo was that simply by increasing the optical lattice depth, one can, in principle, observe the continuous quantum phase transitions from superfluid to Mott insulator phase. This was the idea of Jaxo in this paper. That means the dynamics of the bosons in the optical lattice basically realized the Bose-Hubbard model. This is the Bose-Hubbard Hamiltonian, where J represents the tunnel coupling, U is the on-site interactions. And in the if you load the optical lattice with these ultra-cold atoms, and we can basically control the ratio of J and U by simply changing the laser intensities. So this is the schematic diagram. When the tunnel coupling is very high or the on-site interactions is smaller, that means you have the superfluid phase, which is a compressible and gapless phase, and you can see that is spreaded all over the lattice sides. Now by increasing the lattice depth, that means reducing the tunneling, you can pin the atoms in each side, and creating some insulating phase here. But this mode insulating phase will appear only when you have the commensurate filling, that is the integer filling, maybe 1 particle one side, 2 particle one side, or 3 particle one side like this. We know that the mode insulating phase is an incompressible phase and exhibits the gap spectrum. What? This is the number operator. Operator. What? When we talk about the lowest vibrational states, that means this is the IJ, the just next neighboring sites. Yes, next neighboring sites. No, this is not a disorder. This basically represents the external confinement. Which one? This is the Bohr-Savart Hamiltonian. This represents the, this is basically equivalent to the next neighbor interactions terms, and this represents the kinetic energy terms in the lattice.
Why does it vanish, for example, at 0 or 1? Why does it have that form?
What?
Why does that term vanish if n hat is equal to 1? Why do you want that term to vanish? I'm just trying to understand.
No, when we talk about the mode insulator phase, that means the Ni average is either 1, 2, and 3. Ni average, that is the average number of the particles. And when you have more than one particle, that means the incommensurate, so that corresponds to the superfluid phase. Both the superfluid phase and the mode insulator phase, they are represented by the same Hamiltonian. But when we talk about the superfluid phase, you have the incommensurate filling. Maybe in some lattice there are N1, in the other lattice N1 plus 1, N1 plus 2 like this. And when you have the integers filling, then you have the mode insulator phase. Both the phases are concluded in this Hamiltonian.
But I think he's asking why you are adding Ni minus 1 in the Hamiltonian.
I am not adding anything. This is the standard form of the Bohr-Savart model.
Is that the motivation for that? Why does it have this form?
This is the two-body interactions, next neighbor interactions. So suppose there is the lattice like this. Suppose when one atom tunnels or hops the lattice and comes to here, they may interact, or what can happen? The atom sitting in this lattice, it interacts with the next neighbor lattice.
The minus 1 is on the index there. It's I minus 1. It's not Ni minus 1. The minus 1 is on the I. Is that what you're saying?
Is it a typo?
I think the minus 1 is down there with the I. That's why it's the next neighbor.
That would explain.
This is the next neighbor interactions.
Okay, so the minus
Oh.
1 is
In the index.
Yes, I say that Ni, if it is Ni number of particles, so it will interact with Ni with N minus 1 or N minus. That's the next name, next site.
The index is on the I.
Oh,
It looks like you're making N minus 1. So when the
subtracting
rotation
minus 1.
is
No.
0.
Okay, sorry.
Not in Ni minus
Ni minus 1.
Then you don't need the bracket.
So the minus 1 is to avoid counting the self-interaction between the particle and itself. So you have to
I think what I understand that Ni and Ni minus 1 is basically takes care of everything the nearest neighbor interactions.
Not on the index. Okay.
Eh,
Right. And the
no.
more you have, the more combinations of 2 by 2 that you can do.
Yes,
But
if you
that's like in atomic.
yes, if you suppose if you go in the Harvard model, suppose you consider that, or Harvard model, or suppose I say that, okay, 1, 2, 3 lattice. 1, 2 will not interact, but it is next to next neighbor. So 1 and 3. So it will be Ni minus 1, not, and then Ni minus 2, like this.
That is on the same side. Yeah, no. I think that's on the same side, and there's a huge combinatorics, right? So the occupation number is 5. There's 5 guys that you combine 2 by 2. That's 5 times.
U by 2, it is just to avoid the pairing of the bosons, because this is already there the bosons. So I just take this U by 2, that this factor is already there. So I have already taken care of these pairing interaction terms, just to avoid the double counting. That is already there. Well, and so these phase transitions between the superfluid to mode was basically realized by this benchmark experiment of Greiner and Emanuel Bloch in 2002. Here you can see some absorption images. Basically, they have increased the lattice depth gradually, and it makes the transitions from the superfluid phase to the Mott insulator phase. So the realizations of these superfluid to Mott insulators in the ultracold gaseous atoms, basically the first applications of the quantum simulations, and which tells you that yes, you can basically simulate any kinds of the quantum systems in the artificial setup of the other quantum systems. So that is the quantum simulations, the first observations.
Could you explain this quantum phase transition?
Yes, quantum phase transitions, basically phase transitions in the classical physics, when we talk about there is the temperatures. But in the ultra-cold temperatures is order of the nanokelvin. So at this close to 0 temperature, there is no thermal fluctuations. At 0 temperature, thermal fluctuation vanishes, but there is the, because it is a quantum system, so you have the quantum fluctuations. And these quantum fluctuations can lead to these phase transitions, that is the superfluid.
Could you explain this diagram? What is causing the phase transition here?
Because this is a typical platform. If you go to the classical model, or if you have the high temperature systems, you cannot have these quantum phase transitions. Quantum phase transitions origins is the quantum fluctuations, and the temperatures of the systems, it is ultra low temperatures.
But this is an experiment you are showing.
Yes.
But what is the experiment and what is happening?
Well, they have what they have done this way. This is a optical lattice. It's a 3-dimensional optical lattice, and this 3-dimensional optical lattice was loaded with the ultra-cold 87 rubidium gas. And in the experiments, first they prepare in the optical lattice depth. You can see the first picture is with, they have started with 0, and then go on increasing 3, 7, 10, 13, 14 like this. That means gradually dipping the optical lattice depth. When you dipping the optical lattice depth, that means you are basically reducing the probability of tunneling, right? Optical lattice depth means now these quantum particles, the 87 rubidium atoms, they cannot tunnel out from, they cannot hop out. So now they sit in each lattice. That means this is the insulating phase. So only these transitions is observed. So when you have a shallow lattice, suppose if you have a shallow lattice like this, suppose in their unit this is suppose V0, it is equal to suppose 3 ER. Well, so the bosons here, maybe 3 or 4 bosons, they can hop here, they can hop here. So ultimately, when you have the Bose-Einstein condensation, so you have the superfluid phase which is distributed all over the lattice sides. Now we increase the lattice depth, suppose like this. So now the atoms become trapped here because they cannot jump, because they don't have, it will cost them a lot of energy because this is J. So they don't want to cost this energy to tunnel to the, and to go there. So they like to be sit here, they like to be sit here like this. So that corresponds to an insulating phase. The simple idea is that increase the lattice depth and force the atoms to sit in the lattice site. And that corresponds to an insulating phase.
Idea is that you don't need to heat the system to have a phase transition.
Yes, because I have the platforms is ultra-cold temperatures. Yes.
And classical phase transition you have to heat.
Classical phase transitions will happen only when you have the temperatures.
Yes.
Because the phase transitions originates from the temperature. Here I have the
No, the same temperature you can have a phase
transitions
due to
some quantum fluctuation.
like an external electric field or something else.
When we study phase transitions standard, let's say the classical one, phase transitions always happens with the thermodynamic field. It's a phenomenon. Here when we do these experiments, we have
Not in the optical lattice, but it is just after realizations of BEC, maybe beginning of 2000s. People tried to see that when we talk about the phase transitions, suppose we plot T by Tc here and Cv, it goes like this. So at temperatures T, it is equal to Tc, there is a peak in the Cv, right? But when you repeat these experiments, not in the optical lattice. Suppose I have the simple case of harmonic trapping, right? So suppose I start with 10 to the power 5 number of the bosons and gradually reduce to 10 to the power 3, maybe 10 to the power 2, or maybe smaller, maybe 50 like this. What will happen here? When you have the thermodynamic limit, I think the experiment was by Debra Jean from Colorado, T by Tc. So when you have, what is my thermodynamic limit? If I say this is my thermodynamic limit, so of course I will say this is my finite size system. What will happen in this CV? So in the thermodynamic limit, they get a peak like this. So here you have the ultra-cold Bose condensate. Here you have the classical Bose gas. But now I reduce the temperature. And it is very useful technique that they just pumped out the atoms from the trap and make it a finite size system. And then the CV just pick a hump. And this hump signifies that even at some ultra-cold dilute, the system is dilute, weakly interacting systems, but still it has enormous effect in these thermodynamic properties. And there are many analytical calculations by the group of Dalfabo and Stringari. They basically analytically explain that what will be the finite size shift due to these finite size systems. There are many analytical papers, and later it was seen that when really you talk about the interacting system, the theory of Dalfabo and Stengari, they don't hold for really real interacting systems. Okay, I can proceed. Well, so this is the first observations of quantum simulations, from where we can conclude that yes, the simulations is possible. Now, when we talk about the quantum simulations, our goal is to see that what is going on inside the material. That means you are trying to mimic that how the electrons are dancing inside a solid. So I like to see what the atoms are doing in my systems. So I need to take the photo. And quantum gas microscopy is the fantastic technique to do this. This is a just schematic diagram I took from the paper of Emmanuel Bloch. The sample, it is trapped here in the 2D plane. You can sign this sample, you can fluorescent the samples, and you have the objective here, high resolution objective. This high resolution objective takes the photos. What is these photos? One such snapshot is here. This quantum gas microscopy is able to take the photo of all the atoms. Suppose in this 2D plane I have confined 1,000 atoms. Then you can basically, from these snapshots, you can basically identify each atom positions, and when you know what the individual atom is doing inside the material, you can extract the information regarding what is the entanglement between the atoms, what is the intricate correlations between them, or maybe far above that, whether there is some kinds of the hidden magnetizations or magnetic correlations. So quantum gas microscopy is an ingredient part of this quantum simulation process. Now I must say, I must just give a reference, because this is also a reference problem of Fermi-Hubbard model. Of course, I am not the expert of this Fermi-Hubbard model, but just try to give some overview, what does it say. So this basically Fermi-Hubbard model basically tells you how to realize, how to basically exploit this quantum degenerate Fermi gas to simulate this Fermi-Hubbard Hamiltonian, or simply the Hubbard Hamiltonians. This is the schematic diagram. So spin up and spin down. T, it is the tunnel coupling. When the spin up and spin down, they sit together. They feel some kinds of the on-site interactions. Now it was a long time question that what will be the phase diagram of this Fermi-Hubbard model. No clear-cut answers was there, but people believed that the phase diagrams of this Hubbard model should be somehow related with the phases of the high temperature superconductivity. Well, instead of this Hubbard model, if I just choose the half filling, that means 50% half and 50% down spin, then this Hamiltonian reduces to the Heisenberg spin Hamiltonian. So this is simply the spin-spin interactions. And if I say that ZEX, it is the antiferromagnetic exchange interactions, so you have the antiferromagnetic order. Now this is the experiment which basically done by Keimer group in 2015. And the material is the cuprate material, that is the high TC superconductor. And this is the phase diagram. You can see that this is the zoo of phases. Zoo of phases means you can find out many different phases. I like to point out few things, that in the x-axis there is the doping. When there is no doping in this cuprate material, there is an expected antiferromagnetic order. But when the doping starts, there is the D-wave superconductivity, that means some anisotropy is observed. And there is also some kinds of the pseudo gap. We do not know what is the actual interpretations of this gap, or there is something unusual phenomena in this cuprate material that is a puzzling question for the physicists. But to understand these phases, what we have to do, because when we started doping, there is the whole delocalizations, and you have the antiferromagnetic order in your systems. So you have to understand that how these whole delocalizations interacts with the antiferromagnetic order, and that is a difficult question. But if I come back to the quantum simulations, one can implement these Howard Hamiltonians with this antiferromagnetic spin chain in the platforms of the quantum degenerate Fermi gas. And with this quantum gas microscopy, takes the photos, and then you can have a chance to look at what the holes actually doing inside the material. So that was some idea. That's all, because, yes. Now this is the physics of interacting systems, that what is the recent platform today. It has been greatly revitalized in the past several years, maybe past 1 decade. The usual platforms is the very conventional platforms where you have the contact interactions, or you can have the dipolar magnetic or electrical systems, maybe like some atomic species, like dysprosium, chromium, magnetic atoms like erbium, or one can have the Rydberg dipole-dipole states where the interactions energy can go very high because it's a highly excited states, and also the cavity-mediated interactions, that means the atoms inside this cavity, they can talk some light-mediated interactions. And these are the usual platforms where these quantum simulations, these are the basically the very established platforms like ion traps. I have just mentioned the groups who are basically involved in this simulation process: ion traps, and obviously optical lattice, Rydberg tweezers, and superconducting devices. So with these few discussions, I think I can conclude that ultracold quantum gases can be considered as an artificial solid. We can take that too much flexibility, unprecedented control over experimental parameters, and versatility. It can probe whatever you like almost. So it basically considered as an complementary setup of real solid-state physics. However, the main notions of quantum simulations, the main idea of quantum simulations has been modified, has been revitalized in past couple of years, because now physicists are more interested in quantum science and technology. They like to observe the quantum effect in the quantum matter. Quantum effect in the quantum matter. It means that we have the abstract quantum systems as a simulator, but this abstract quantum system is not identical of the quantum systems you are going to probe. This is a completely independent quantum systems. It has own properties, and these properties may be challenging. So when we study this simulator, let it take it as a completely independent quantum many-body systems. So the whole idea has been changed, and it has opened a new area of research where we talk about the quantum many-body physics with ultracold gases. So it reminds me the vision of Feynman, maybe several decades back. His idea was like this, that when you are basically implementing some abstract quantum systems in your laboratory, it opens the area of study of quantum many-body physics. Now with this rapid development with the experiments, what is the situations as a theoretical point of view, and what kind of the many-body method can take care of such highly correlated systems. So this is the Hamiltonian, and this is the trapping potentials. This is the two-body interaction strains. So generally, according to the experimental protocols, according to the types of the systems, we have to choose the Hamiltonians. You can put some time-dependent modulations in the potentials also, but when V of R is periodic, we say that this is the quantum simulator for the lattice models. Solving the many-body Schrodinger equations, if I solve the time independent, we can have the different kinds of the ground state properties, and time-dependent Hamiltonian gives you the dynamical features. Now, the different kinds of the numerical approaches to solve these quantum many-body systems of the ultracold atoms, bosons and fermions, or their mixtures, there are different approaches. I like to broadly classify them into two categories. When we talk about tight binding approximations or DFT, before doing anything, we approximate the Hamiltonian. But when we talk about the Gross-Pitafevsky equations, quantum Monte Carlo, or the multi-configurational time-dependent Hartree, which we utilize for our simulations, we do not restrict the Hamiltonian. We keep the Hamiltonian as it is. We restrict the state according to our requirement and according to the challenge in numerical convergence. That's all. Now, little bit more about multi-configurational time-dependent Hartree. I just tried to make some pictures. Multi-configurations means in your setup, there are many interacting particles. Multi-configurations means we have to expand the wave functions in the linear combinations of all possible configurations. Time-dependent means if this is one possible configuration at time t is equal to 0, they will change with time. And Hartree means this is the product of single particle functions. But the important point is this change in the configurations with the time. And this is the hardcore part of time-dependent multi-configurational Hartree methodology, because it can take care of the correlations when you allow the systems to evolve dynamically. I will explain in little bit details. Well, so multi-configurational time-dependent Hartree, it was developed by the research group of Professor Lorenz Sederbaum, and also there are huge contributions coming from Ophir Allen and Alex Stelstops. Here I just like to refer few of their pioneering work. These are the references. Let me briefly summarize here. This is our Hamiltonian. I put some Heaviside wave function just to explain that it will be off when we are trying to solve the time-independent Schrodinger equation. These functions is required when we try to solve the dynamics, that is the quench dynamics. Anyway, time-dependent solutions mean H psi is equal to I del psi del t. In the time-dependent Gross-Pitafevsky equations, the psi is decomposed as the product of the single particle functions, and it is well suited to describe the condensations. When we are sure that all particles, they can be described by the single particle state. But when we talk about the strongly correlated many-body systems, it is obvious that this single particle orbital is no more a good approach, because the many-body state may be fragmented. That means many orbitals can be significantly occupied. And that is the starting point of MCTD-HX. X means when it is B, that stands for bosons. When it is F, that stands for the fermions. So we have the same decompositions, so only we change in the symmetrizations or anti-symmetrizations when we do the simulations. Here? Yes, this is basically the permanence. That means, suppose you choose n particles with the m orbitals. So what will be the number of possible configurations? It will be like this. If I'm not wrong, this will be something like this. So,
Okay, so they are single particle, they are, let's say, later determinants, so to say, of single particle.
yes, and the efficacy is, now the coefficients has the time dependence. So you start with the initial coefficient, and that will change with time. You start with the orbitals in your initial state, but these are not the fixed orbitals. We have that, we put the time dependence there. So during the time evolution, what you can expect, that many excited states can participate in the dynamics. So when you have the fixed orbitals, it cannot take care of this effect. It will remain same all throughout the time. But when you have the time dependence in the orbitals, so they can appropriately accommodate that how many orbitals is participating in these dynamics.
So, for example, the time element is coming from the superposition of many n.
Yes.
Each ket per se is not
Yes.
stable.
Yes.
It's not
Yes.
stable.
Yes. 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 And for the fermion, this is the simply the Slater determinants. This is the number of. I will show you some pictures later. N basically here tells that the configurations of the Hilbert space. And this number of the configurations is here. N ket means you are distributing n number of particles in m number of orbitals. So the total number of configurations will be determined by this mod. Yes, this basically tells the how many number, what is the configurations of the Hilbert space during the computations. This are, yes, this basically the configurations of the Hilbert space. We put it as, suppose, how to say, N1, suppose one state is, suppose I have 3 particles. I can put 1, 1, 1, 1, 0, 1. This is the simple way we do the statistics. So now we have n particles in the m orbitals. So this is the takes care of all possible configurations. And the number of configurations is there. And n.
No, I'm asking what is the n vector, that thing? This is the n is, what is n and n vector?
N, it is the state of permanence. We call it is the state of permanence. That means how you are basically arranging the number of bosons or number of fermions in different orbitals. That is take care of in N. I will show you some pictures later.
How many components it has?
Yes, n plus m minus 1 m. That is so. This is n c n. This is simply the combinations rules. N c n minus m.
So here the complexity is still horribly hard. There is no approximation yet.
No approximations, no approximations. Only I have to, yes, I have to approximate only when I restrict the number of orbitals. So
the moment is still horribly hard, is scaling badly with the number of particles, all the stuff that you have.
yes. So the next calculations is straightforward. I am not going to make it delayed or maybe lengthy. That is the simple way we do the time-dependent variational principles for both time-dependent coefficients and time-dependent permanence. And finally, we are left with a set of coupled set of equations which we have to solve simultaneously. There are many tutorials which basically tells you that how this software works. It's a huge calculations. When I started to work in this field, it took several months to repeat the analysis of Ophior and Stelstops. It was very hard, but when one starts to work, one has to pass all these analytical calculations, how to do these time-dependent variational calculations and everything. Okay, let me come up with the actual physics that what we are getting here. So when we have the number of orbital 1, no doubt, we get back the Gross-Pitavetsky results. But when we have m tends to infinity, so the number of permanents basically spans the complete Hilbert space. So we can claim that multi-configurational time-dependent Hartree is exact by constructions. But during the simulations, we basically cut the number of the orbitals. We do the simulations with increasing number of the orbitals. And when we see that the last orbital occupations, that is, when you increase the orbitals, if the system is fragmented, then the orbital starts to populate. And when we see that the occupations in the last orbital becomes insignificant, and all my measurements are remain invariant, we conclude that, well, now we have the converged results, and we talk about that this is a numerically exact results. This is some points I like to flash, that this is numerically exact. I told you. It is highly versatile because it can take care of bosons, fermions, and also multi-component particles. The hallmark of pensility HX is the fragmentations. That means you can follow how the orbitals become fragmented with time. Sometimes we talk about the dynamical fragmentations. And the most important point is that MCDT HX is very efficient to probe the out of equilibrium dynamics. And also it is supported by high performance computations like MPI and OpenMP. We also have the appropriate algorithm. That was the paper of Kasper Sackmann in Nature. Probably it was 2017 Nature paper. I forgot to quote his paper. This was the big algorithm which basically tells that, yes, these single shot simulations is possible in this methodology where that can catch the single shot readout of the experimental images. Now the next questions, which parameters, which measurements we can basically have? Of course, we can have all the conventional measurements, but I like to specify that it can measure the global correlation function, and that is the most efficient point to know that how much correlations is in your many body systems. And in some of my papers, a little bit early, couple of years back, even we have found some kinds of the dynamical evolutions where we are able to show that even the third order correlations is important. So the efficacy of MCDT HX to calculate any order global correlation functions, and there are 2 papers in archive, maybe last December 2024. Maybe those papers are already published. In the experiment, in the gas microscopy experiment, now people can measure these correlations functions of any order. At least probably they measured first order and second order correlations. I also try to mention one more thing before I move to my calculations, that results that as I told you right now, that multi-configurational time-dependent Hartree is very much efficient for the out of equilibrium dynamics. That means you prepare one systems in the initial state, and suddenly you change one parameters in the Hamiltonian and let it evolve. Let it evolve. That means the system is going far out of equilibrium, and the natural question is that how the systems will relax in the long time evolutions. There are many possibilities. The systems can thermalize, the system can evade thermalizations, or the systems can exhibit some quasi-thermal state before reaching the actual thermalized state. So this is a very complicated out of equilibrium scenario. when we started to work, we found that the information's entropy is a very good measurement to understand this out of equilibrium dynamics. And the kinds of information's entropy people like to use, that is von Neumann entropy, Shannon information's entropy, and these days we have the entanglement entropy also. But we found that as MCDT wave function decomposed in the time-dependent wave coefficient and time-dependent permanence, we can basically give different versions of the many-body information's entropy, and these information's entropies have no counterpart in the mean field theory. This is the coefficient Shannon information's entropy determined by these expressions. It tells about that during this time evolutions, how the many-body systems it is being delocalized in the Hilbert space. Coefficient inverse participation ratio known to us is basically an important quantity to understand the chaotic dynamics. N-body coefficient entropy was the hybrid versions of the coefficient Shannon information's entropy, but it takes care of the two different kinds of the configurations. And another is occupational Shannon information's entropy that is defined by these expressions. So this is the basically tells about that how the different orbitals are being populated with time. When we do the mean field theory, there is only one coefficient. So SC is trivially 0. And also the number of orbitals is basically 1. So occupational entropy is also 0. So these three quantities have no counterpart in the mean field theory. Now come to my research activity. My research area is mostly concentrated only about the strongly correlated many-body systems. Should I stop? Then I cannot present my any results. Should I? Well, so just let me quickly wrap up my present research activities. As I told you that my research basically concentrated on the strongly correlated many-body systems. And this slide tells some of my recent calculations, especially going beyond Bose-Hubbard physics and beyond mean field theory. Just like to tell you that these calculations mainly on the disordered lattices, but for the contact interactions. And we have obviously observed some unusual localization process in the disordered lattice, and some quasi-phases in the disordered lattice. I'm not going to present any of them because these are the contact interactions. This is a quick overview of my present research work on the out of equilibrium dynamics, where I have basically observed the out of equilibrium dynamics in versatile platform and tried to understand that what is the internal mechanisms and what is the time scales of this relaxation process, how the relaxation happens. So these are the different platforms. Most of them basically takes care of contact interactions or weak dipolar interactions. But in several years, last several years, you know that the quantum simulation platform has been changed rapidly for the long-range interacting systems. Long-range interacting system exhibits different exotic quantum phases like supersolid, droplets, quantum spin, liquid. But the most important thing is the robust entanglement, long-range correlations, and the evade thermalizations. This is very important point because these long-range interacting systems, or basically I would say that the broader area of atomic, molecular, and optical systems are at the cuffs of the quantum science and technology. Because when a system evading thermalization means you have the long-lived excited states where the quantum informations can evade decoherence. And that is the requirement of the quantum information task. And that is the reason why the quantum simulations since last couple of years has been concentrated on these kinds of the atomic species and the dipolar molecules. I like to flash very quickly a few of my results. In this paper, we have tried to mimic some experiments of Heller, where he made some, observed some exotic dynamics. That means the quench process is exotic, means you have a strongly repulsive gas and you quench suddenly to the strongly attractive gas. Well, this is my interaction state, and I put this alpha means we have the generalized long-range interactions. And you can see that the interaction strength is so strong. This is for the bosons and this is the fermions. We have only 5 particles. It is an enormous cost of numerical convergence. So we are able to handle only 5 particles and just reproduce the Heller's experiment. Of course, we have very exotic features which is not observed in Heller's experiment. Here we have plotted the orbital occupations. You can see that we have made the computations with 5, 10, 15, 20 orbitals. In this regime, you have the TG gas, and for every simulation, irrespective of how many orbitals are there, first of all, at the first point we thought, oh, this is a numerical convergence. We tried a lot to understand, and then we realized, no, it's not a numerical convergence. Actually, at this time, the strong gas collapses to the super-strong gas, and the most important point that at this post-quench state, the STG gas occupies all the available of orbitals, 10 here, 20 here. They are equally distributed within these 5 bosons or 5 fermions. We call it as the violent orbital fragmentations. We also observed when we plot the coefficient as a function of Hilbert space number, it changes from 120 to 40,000. You can see it. There is a chaotic delocalizations in the Hilbert space. And at the same time, we also observed some unbounded productions of entropy. So there are many other, it's a huge paper. Just I like to focus the findings of our paper. So the TG gas means we have some kinds of the non-thermal quantum gas. And by these simulations, we established that this STG gas is the classical gas, because it exhibits chaotic delocalizations and unbounded productions of entropy. And they are separated by this exponential boundary. There is universality of dynamics between bosons and fermions. But this is an important observation. Alpha, it is the generalized long-range exponent here. And we have tackled the alpha from 0.5 to 4. Our system is one-dimensional. We are reducing alpha below 1 just to observe that whether it exhibits some new exotic features or not.
Because you cannot read the dipolar interaction exactly.
What?
Why do you have this chart? You don't get the dipolar interaction exactly.
This is a 1D. This is a 1D. We don't have these dipole-dipole angular interactions. The Heller's experiment is also 1D. This is also 1D experiment. Well, but this is an important observation. If I concentrate on these entropy evolutions, here we just flash one results here. Instead of quenching GD from 100 to minus 100, I just gradually reduce to minus 80, minus 50, minus 30, and minus 10. You can see that the stiffness gradually decreases. And here, I can create some kinds of the very slow or plateau region. And that is the most important observations, that fine-tuning of GD can basically result to obtain a plateau. Plateau means before going to the saturations at longer time, the system will stay there. It is a highly exotic state, but you can confine them for some time. And this is the major informations in the quantum informations processing, because you are holding this quantum informations in this excited state. I am not going to get other pictures, just to conclude that this is a blueprint. These results one can take as a blueprint, as a quantum tool, just for the future quantum information task. My next work, very recent work, where we have also tried to establish some TG to STG quench following the very important research paper of Cow, where they also exhibited the evading of thermalizations. Well, this is my system. This is an 1D lattice. But now I have the short-range interaction, and the system is supplemented by some dipolar interactions. Dipolar means now alpha it is equal to 3. Yes, according to Cow's research papers, when GD it is positive, we can stop this collapse from TG to STG. But our calculations also give some nice physics where we go beyond this Cow's results. Our motivations is to understand that is it possible to provide the quantum information that, well, this is my zone where we can have some excited states with high fidelity, right? So we have did the simulations with GD negative. Now GD is very small negative here. You can see that the state is completely retained. There is no collapse. Here, it doesn't collapse, but some kinds of cluster formations is there. When GD is negative, then collapse happens. The important observations is here. I just try to explain in terms of the fidelity. What is the fidelity? Fidelity is basically an important measurement which tells that you start from an initial state. What is your initial state? This is psi 0. Then you do the quench and let it evolve. So psi t, it is the time-dependent wave function. When you take their overlap and the modulus are square, it tells that whether during this dynamics your initial state collapse, or they reorganize, or they hold. What is our results? You can see that this is a single filling case, that one particle, one lattice. Yes, we have the GD values, negative values. We have a high fidelity regime. That means even the quench is very exotic, but still we have the excited states and have a huge high fidelity. That means the system is retained for a longer time. You have seen in the other case that the time is 944 microsecond, 177 microsecond. This is the time to hold this excited state. Here the fidelity drops. That means the initial state reorganized. And here the fidelity is 0. We cannot do anything. That means the initial state is completely reorganized or maybe just collapsed. Just increasing the filling factor, we can see that this high fidelity zone disappears. And there is a small fidelity zone and 0 fidelity zone. There are many, it is also in huge papers, and here also we have systematically analyzed the correlation dynamics and many other features. But let me conclude by saying this, that this work basically tells you that how to harness the dipolar interactions with the appropriate quench protocol such that I can have the excited but metastable state where the fidelity is either very high fidelity or smaller fidelity zone. So this is an important information for the quantum information processing. This is my last work. Just a little bit recapitulate this. For this paper, we received very, very good feedback from the referee of physical review research. They asked just to work some on language. We have resubmitted very recently. This is a nice work where we have shown that, well, now this optical lattice has some disorder. What is the role of these dipolar interactions? Disorder means this is a quasi-periodic potentials because you have the primary lattice and you have the secondary lattice here. The beauty is these quasi-periodic optical lattice exhibits long-range order. Dipolar bosons also exhibit long-range order, but which is unexplored physics. But it is very important physics for the quantum simulations in the quantum information processing, that what will happen if we put these dipolar bosons in this quasi-periodic lattice, because now both the long-range order will try to compete. Just briefly summarize few pictures that you can see that we have the crystal phase. These are the known phase to all of us, superfluid and mode, but we have the dimerizations here and this crystal phase here, 1D crystal phase. And the most important point, this crystal phase remains robust even when the VD is very high. We know that when you have simple weakly interacting bosons in the lattice, introducing disorder, it will lead to the Anderson localizations. Or for very strongly interacting system may exhibit the many body localizations. But here we have the 1D crystal order which remains robust. And here you can see that incommensurate filling, I have 8 bosons in 5 lattice. You can see this is not a crystal state. This is density wave pattern. You can see, I cannot see properly, but I can tell you the distributions is 2, 1, 2, 1, 2. 8. So this is the density wave pattern that also remains robust in the disorders. The same physics can be drawn in these phase diagrams also, that the superfluid phase is extended, but the crystal phase remains robust. Charge density wave phase remains robust. And what does it tell? It gives a very important information that resilience of this crystal order, resilience of these density wave patterns in the disordered lattice may serve as an important platform of many body localizations for more strongly correlated systems. So I conclude here that long-range interactions already enhance the computational platforms, and we are able to at least to present some interesting physics with these dipolar interactions, how to harness dipolar interactions in quantum simulations. And our ongoing research activity is with light-mediated interactions, how to harness the tailored dissipations, and also going to multipolar, multiband with the dipolar physics. I have no more time to describe this, but this is just a flashing slides that this is our recent works. It's not the single band Hubbard model. Just go to the upper band model and try to correlate these continuum systems with this discrete band model. And also we are working to optimize our quantum technique. This is my ongoing research activity. So this is the summary. Our main work is on the dipolar interactions, and we are investigating the appropriate experimental protocols such that we can give important informations for the future experiments. And of course, I must acknowledge the significant contributions from these researchers, professors, who have enormous contributions in my research activity. And to continue this research activity for a long time in different research groups, it was possible because I held these positions as ICTP Italy for 6 years. Also, I am attached with them. So it's thanks to ICTP also for this offer. Well, so thank you. I am going back, you just tell me. stop me. No. This is, we like to see crystal phase, so the minimum filling factor should be 2, right? So you have the 6 bosons in 3 lattice sites. So 2 bosons is here, 2 bosons is here, 2 bosons is here. So this is the mode phase, no splitting. It is a density pattern. So 2 bosons here. Here you can see that complete splitting doesn't happen, but they start to just like this. That means you have this lattice. This is the lattice. You have 6 bosons. So initially, mode means you have this with 2. Now, when you have stronger GD, go to right side. This is the fragmented mode. That means this is the fermionized. 2 bosons sitting in the same lattice, they try to escape their spatial overlap. So fermionization happens. And in the crystals, the complete separations, 6. Complete isolations. So this is the 1D crystal phase. It's different from the 3D. It's a 1D crystal phase. And these crystal phase remain invariant to whatever disorder you give. It's not many-body localization, but this is the robustness of the system. And the underlying physics is the strong many-body correlations inside this crystal phase. We have the correlations graphs also in this paper. I have no time to present, but this is the underlying mechanisms. That this is, you cannot observe this physics in the Bois-Hubbard model, because Bois-Hubbard model cannot take care of long-range order. If you do the simulation, suppose you try to make the exact diagonalizations of the Bois-Hubbard model, you will never observe this phase, because Bois-Hubbard model can take care only nearest neighboring. It cannot take the long-range order like this. So for the strongly correlated states and the different features, we are trying to give some informations to the quantum informations processing, either dynamically or some static pictures, as much as possible, because we are bounded by the numerical convergence also, quite high number of orbitals are required to have these converged results. We have the heat map. We have shown that how the interactions energy, kinetic energy, potential energy, they compete just to describe these phases. That is the heat map phase diagram. Referee also praised a lot about this paper, that it said this is a wonderful, but there is some problem in the language, so we changed the language and we resubmitted to again the physical review research. Many-body localization is that, localizations means you try to trap some particles. Many-body localizations means you have the disorder potentials. When you have very strongly interacting particles and strong disorders, then it happens that switching on the disorder, the system doesn't, you can plot the imbalance, or you can plot the entanglement entropy like this. So it should go like this. So this is the saturations means, if you measure some observables at this point, the value can be determined by its thermal value, the thermalization. But when the system exhibits many-body localizations, if you plot S of t, any entropy, maybe entanglement entropy with t, you cannot plot with t. You have to plot with logarithmic of t, because it's just slowly. Suppose here, in arbitrary unit, I put the time t, it is equal to say 1.0. Here, it's slow increase. I I have my results, so I can tell you the time should be maybe order of 10 to the power 3 in the same time unit. And then slightly increases, logarithmic increase, but it never goes like this. That means many-body localizations means the systems is unable to reach the thermalizations process. And this happens only when you have the strongly correlated, strongly interacting particles in the disordered lattice, which doesn't exhibit Anderson localization, doesn't exhibit thermalization as well. But you see, there are many things. Suppose when I write the Hamiltonians in the many body, there is the kinetic energy, there is the trapping potentials, and then Vij, right? Interaction states. You see, I give you one example. Suppose this is my many-body Hamiltonian. When I do the simulations, I can change this trapping potential, that is my lattice potential. I can also change this two-body interaction strength, right? If you go back to the Bose-Hubbard physics, then they change everything by the ratio of J by U. So they talk about the mode phase like this. Right? Right? And now if you switch on the disorder, this mode insulator phase and the superfluid phase is intercepted by the Bose-Glass phase. Bose-Glass phase. But in our many-body calculations, we have some works where we have shown that if you have the mode state like this, which is determined by the large V trap and small lambda, suppose lambda is the strength. This may happen. You may also have like the same mode state. You cannot distinguish because their one body density is same. But now I prepare with small V trap, small trap, large lambda. Then, what is the difference? If you do the same simulations with the Bose-Hubbard phase, Bose-Hubbard physics, you cannot understand this. But in our many-body calculations, we have shown that when you have small lambda and V trap, then this mode phase will respond and exhibits the Anderson localizations. But when you have the smaller trap but larger interaction strength, the many-body correlations is significant. And this mode state is so robust that it doesn't exhibit any kinds of change in the correlations. If you plot the correlations, the amount of correlation, this is density, they are identical. You cannot distinguish them. But now I switch on. Now I switch on the disorder. Vd, same, Vd not equal to 0. Vd not equal to 0, same Vd. But it will respond. It will move to Anderson localizations. Maybe from this you will have some like this, Anderson localization. But this, no. This doesn't respond. Maybe what we have observed that if you plot the one-body correlation function, there is certain change in this which you cannot detect. You cannot observe what is the change in the density. If you plot the correlation functions, then you can observe that this is the mode correlation. These mode correlations become slightly melted due to this disorder, but it doesn't go to this Anderson localization. Yes, so this is the, no, but I like to say that you have the mode. You have the mode. But when we do the many-body simulations with changing different parameters, so that is I like to say that if you see this one-body density and if you say, okay, I put it in the disorder potential, one system will respond, one system doesn't respond. But when the Anderson localizations, or in 2008, the Roartis experiment, the first experiments of Anderson localization, that was either non-interacting or the weakly interacting systems. But if you do the simulations with strongly interacting systems, you will get different physics. My belief is, you see that from the theoretical point of view, there are some calculations, but there is no concrete answers. No concrete answers. You are not 100% sure that, okay, these systems will exhibit the many-body localizations. There is no concrete answers. People are trying to even, okay, when the people, the theoretical people, they started to work on it, they thought, well, entanglement entropy is the appropriate quantity to tell about. Then they tried to plot the imbalance in the different lattice. We have done also imbalance, but they found, maybe in, I forgot the reference, there is a very important paper in Physical Review B last year just. They have basically, it's a huge paper, and they have basically present many numerical results, and they clarified that how the concepts of entanglement entropy as well as the imbalance, they don't fit in diverse situations. In diverse situations means weak strength, strong disorders, weak, or strong weak. There are many calculations, but there is no confirmations yet. No confirmations yet. And there are many papers in PRB also, because you are not sure that what is the origin of this many-body localization. That we must know, that who causes many-body localizations. So these are the supporting documents, supporting features that we are representing, that this is the features of many-body localization, but we do not know what causes many-body localizations. You see, my systems, my system has no noise, no dissipations. Even there is no dissipations. It's a completely isolated system from its environment, or have minimal coupling with the environment, so there is no dissipations. We talk about that during this dynamics, of course, by nature, every system will go to the relaxed state. You cannot avoid that. Only we do not know when they will relax. We are not interested in that one. We are interested whether you can have this excited state which retains for some time. That means if you plot this entropy, if it go on increasing, there is nothing. You cannot hold it. If you plot the entanglement entropy here as a function of t. But there are many papers which shows, there are the first experiment, 2013, the L. and Gong's experiment, New Journal of Physics, 2013. That was the first experiments with the ion trap systems, and they exhibited that if you plot the correlations, suppose pair correlation functions, like if I plot Cij average as a functions of time, or maybe interaction states, whatever it be, then correlations functions. First, there is some kinds of the plateau. Suppose I like to draw it in like this. This is the plateau, and then they go up, and they do like this. That means correlations is whole for certain time. And this is the avoiding of decoherence. The amount of coherence retained in some excited state is the input for quantum information processing. That means you are holding the informations. And that is the input of quantum computing. So we like to, our interest is not to see what is going on for a long time, nothing. we like to know that what should be the system, what should be the interactions. Is it atomic? Is it molecules? Is it pure contact interaction or dipole? How we will change the interaction strains such that we can have some exotic and quasi-thermal states. If it thermalizes and nothing will happen there. We need the intermediate plateau. This is the important part. And how you can simulate this intermediate plateau. That is the work I have tried to demonstrate in few slides. At least we are able to give some informations. Well, and all these informations we get in the 1D systems. The reduced dimensions is the first thing. The reduced dimensions where the and finite size. Because if you go, the origins of all these phenomena, there is the quantum fluctuations. And these quantum fluctuations is really predominating when you have reduced dimensions and finite size ensembles. We are not interested what is happening in the thermodynamic limit, whether the system, what is going on in these thermalizations. No, we are interested only in these exotic dynamics. Strong interactions, strong correlations, such that we can give some informations that how to set up future experiments.
So, for example, if I wanted to study that time that the system stays in between, could I like something a noisy, random electronic that can come and then study this time before it reaches synchronization? Is this model capable of doing that?
It depends because, you know, introducing disorder means the way I have done, introducing some additional lattice, but also you can add some random potentials. We didn't check that with any random potentials that whether we can simulate the same physics or not. Because random potentials means you are introducing disorder in each lattice points. So that I don't know. Maybe even this model cannot take care of your problem. We have to add some additional dissipation terms in the Hamiltonian. And we are working on that where we talk about the light-mediated interactions in the cavity.
Okay, thank you very much. Does anyone know how to not try? Switch off?